Imagine the world in late August of the year 1859. It was a time of profound and rapid change, yet in comparison to our modern era, it was a world of quiet simplicity. Great steamships, powered by coal and puffing thick black smoke, were charting the oceans, connecting continents in a way that would have been unimaginable just a generation earlier. On land, the rhythmic chugging of locomotives echoed across continents as thousands of miles of iron rails were laid, stitching together cities and frontiers. This was the age of steam and iron, a period of bold engineering and burgeoning industrial might. Communication, too, was undergoing a revolution. The fastest way to send a message across a great distance was no longer by horse or by ship, but by the electric telegraph. A network of thin copper wires was being strung across landscapes, a fragile web that carried messages as a series of electrical clicks. For the people of 1859, this was the pinnacle of technology, a system that seemed to conquer time and distance. It was the internet of its day, a marvel that connected businesses, governments, and individuals with astonishing speed. But for all this progress, humanity's understanding of the universe was still in its infancy. Our planet felt vast and secure, and the heavens above was seen mostly as a clockwork of predictable, distant bodies. The sun was a reliable source of light and warmth, its face occasionally marked by small, dark blemishes that astronomers called sunspots, but otherwise considered constant and unchanging. Nobody on Earth knew that 93 million miles away, a storm of unimaginable scale was brewing. On the surface of the sun, immense magnetic forces were twisting and straining, building up energy on a scale that dwarfs any terrestrial phenomenon. An area of sunspots, a complex and volatile region, had grown to an enormous size and was crackling with power. It was a loaded gun, pointed directly at our planet, and no one had any idea it was about to fire. This podcast is the story of what happened next. It is the story of the largest solar storm ever recorded in human history, an event so powerful it set telegraph offices on fire and produced auroras so bright that people could read newspapers by their light in the middle of the night. It is an account of a moment when the sun reached out and touched our world, not with its gentle warmth, but with a violent electromagnetic fury. This event, known today as the Carrington Event, was a spectacular and disruptive episode in the 19th century. The story of the first ever observation of a solar flare, the celestial event that would herald the great storm, begins with the quiet dedication of a single man. His name was Richard Christopher Carrington. Born in 1826, Carrington was not a professional astronomer in the sense that we might understand today. Instead, he was the son of a wealthy brewer from the town of Brentford in England. The family business afforded him a comfortable life and, more importantly, the financial independence to pursue his true passion: the meticulous and systematic study of the stars. After studying at Cambridge, he briefly held a position at the University of Durham's observatory, but he soon decided to strike out on his own. He wanted to work without constraints, to focus entirely on the astronomical questions that fascinated him most. To this end, he used his personal wealth to build a state-of-the-art private observatory at a place called Redhill, in the county of Surrey. It was here, surrounded by the English countryside, that Carrington dedicated himself to a monumental task. He was determined to improve the world's understanding of the sun. At the time, while astronomers had been observing sunspots for centuries, ever since the invention of the telescope, their nature was still a subject of much debate. Carrington embarked on a painstaking project to map and track the daily movements of these dark blemishes on the solar surface. Day after day, whenever the notoriously cloudy English weather permitted, he would be at his telescope. He employed a technique known as projection, which was both safe and effective. Instead of looking directly at the sun through his telescope, which would have instantly and permanently blinded him, he used the instrument to project a large, detailed image of the solar disk onto a white screen. He could then safely study the image and carefully draw the positions and shapes of the sunspot groups, creating a meticulous record of solar activity. This was his routine, a quiet and methodical pursuit of knowledge. The morning of Thursday, September 1st, 1859, began like any other. The skies over Redhill were clear, and Carrington was at his post in his observatory, projecting the sun's image as usual. He was focused on a particularly large and complex group of sunspots that had been visible for several days. This region was a tangled mess of dark patches, indicating an area of intense magnetic activity, although the physics of this were not yet understood. Around 11:18 in the morning, as he was sketching the sunspot group, something extraordinary happened. Suddenly, and without any warning, two intensely brilliant patches of white light appeared within the sunspot cluster. Carrington himself later described them as being of surpassing brilliancy. This was not a subtle change. They were dazzling points of light, far brighter than the surrounding surface of the sun itself, which is already blindingly bright. Carrington was, by his own account, completely taken aback. In his years of solar observation, he had never seen anything remotely like this. His first thought was that perhaps it was an instrumental error. He wondered if a beam of sunlight had somehow penetrated the filters or screens he was using, contaminating the projected image. He was, as he put it, in a state of great surprise. He quickly checked his equipment, but everything seemed to be in perfect order. The 2 points of light were real. Realizing he was witnessing a truly novel phenomenon, his scientific instincts took over. He knew he needed a corroborating witness. He ran out of the observatory room to find someone, anyone, who could come and see what he was seeing. But the search was frantic and ultimately fruitless. He couldn't find anyone quickly enough. When he returned to his telescope just a minute or so later, the spectacle was already fading. By 11:23, a mere 5 minutes after they had first appeared, the two brilliant patches of light had vanished completely. The sunspot group looked just as it had before the event. It was as if nothing had happened. But something profound had happened. Richard Carrington had become the first person in history to knowingly witness and record a white light solar flare. Although he couldn't have grasped the full implications at that moment, he immediately suspected that this was a significant event. He carefully noted the time and the exact position of the flare on his drawings. In the hours and days that followed, as reports of strange magnetic disturbances and auroral displays began to pour in from around the globe, Carrington made a daring intellectual leap. He suspected a connection. He later presented the paper to the Royal Astronomical Society, where he cautiously proposed that this brief, brilliant flash on the sun might be linked to the subsequent geomagnetic storm on Earth. This was a revolutionary idea. The notion that an event on the sun could directly and almost instantly affect our planet was not widely accepted. Carrington's observation and his bold hypothesis laid the crucial groundwork for the entire field we now call space weather. In the world of science, a single observation, no matter how compelling, is rarely enough to establish a new fact. Independent verification is critical. As it turned out, Richard Carrington was not the only person to see the great solar flare of September 1st. About 150 miles away from Red Hill in London, another amateur astronomer was also observing the sun at that exact time. His name was Richard Hodgson. Hodgson was also a man of independent means, and, like Carrington, he had a passion for astronomy. On that same morning, he too was using his telescope to project an image of the sun, and he too was sketching that very same large group of sunspots. And at the same moment as Carrington, he saw it. Hodgson described it as a sudden outbreak of light, which looked like the star Sirius, the brightest star in the night sky, suddenly appearing on the solar disk. He was just as surprised as Carrington was, initially thinking his eyepiece was out of focus. But he quickly realized he was seeing a genuine event. His account, recorded in his logbook, matched Carrington's in almost every detail. The time, the location on the sun, the intense brightness, and the short, 5-minute duration. The fact that two independent observers, using their own equipment in different locations, saw the exact same thing at the exact same time was irrefutable proof. This was no trick of the light or instrumental glitch. This was a real, physical event that had taken place on the surface of the sun. When their reports were presented to the Royal Astronomical Society, they caused a sensation. The corroboration provided by Hodgson was the final piece of the puzzle, cementing the discovery in the annals of science. Together, the meticulous drawings and careful timings of Carrington and Hodgson provided the first ever scientific record of a solar flare. They had opened a new window into the violent and dynamic nature of our star, and they had, without knowing it, documented the opening act of a storm that would soon engulf the entire planet. Just 17 hours after Richard Carrington and Richard Hodgson witnessed that blinding flash of light erupt from the sun's surface, the unseen consequences began to manifest on Earth. Throughout the day, reports of strange phenomena started to trickle in. Compasses went haywire, showing erratic fluctuations. Telegraph operators noted unusual currents on their lines, making it difficult to transmit messages. But as darkness fell across the globe, the truly spectacular and bewildering impact of the solar storm became visible to everyone. The sky ignited. What unfolded that night was an auroral display unlike any seen in recorded history. For most people in 1859, the aurora borealis, the northern lights, was a rare and beautiful spectacle, visible only in the extreme northern latitudes, places like Canada, Scandinavia, or Siberia. The aurora australis, the southern lights, was equally confined to the Antarctic regions. But on the night of September 2nd, these ethereal curtains of light descended to latitudes where they were almost never observed. Reports flooded in from across the world, describing skies ablaze with vibrant reds, greens, and purples. From Europe to Asia to North America and down into the tropics, people stared up in a mixture of awe, wonder, and sometimes outright fear. In the United States, observers as far south as Washington, D.C., and even in Cuba and Jamaica, reported seeing the lights. In Havana, Cuba, the typically clear night sky was filled with a red glow that shimmered and pulsed. One newspaper reported that the phenomenon was seen across the entire island, leading to widespread astonishment among the populace. Even in the far-flung reaches of the Pacific, on the Hawaiian Islands, people reported brilliant displays of celestial light. This was unprecedented. The Earth's magnetosphere, our planet's protective shield, was being buffeted and overwhelmed by a torrent of charged particles from the sun, and the result was a global light show of epic proportions. Imagine the scene. Farmers in the American Midwest, fishermen off the coast of New England, gold prospectors in California, and shepherds in the Australian outback, all looking up at the same dazzling, impossible sky. Many had no frame of reference for what they were seeing. Some were convinced the world was ending. Others, more romantically inclined, wrote of angels in the heavens or signs from above. The lights were so bright that in many places people were able to read books, write letters, or conduct conversations outdoors without the aid of lamps or candles. In Boston, Massachusetts, one newspaper reported that the entire city was illuminated with a soft, reddish light, enabling people to navigate the streets as if it were twilight. Telegraph operators, who would soon become very familiar with the storm's more disruptive effects, often paused their work to gaze at the spectacular crimson and emerald hues dancing above them. The sky, usually a backdrop for the familiar stars, had become the main event, a living, breathing canvas of solar energy interacting with Earth's atmosphere. The Carrington Event's most immediate and concerning impact was on the technology that was beginning to shrink the world: the electric telegraph. In 1859, telegraph lines crisscrossed continents, linking major cities and even some remote outposts. These wires carried electrical signals. The system was robust for its time, but utterly unprepared for the extraterrestrial assault it was about to endure. As the geomagnetic storm intensified on September 2nd, the telegraph lines themselves began to act as massive, unplanned antennas, picking up enormous electrical currents induced by the fluctuating magnetic field of the Earth. These currents, known as geomagnetically induced currents or GICs, were far more powerful than the faint signals the telegraph operators were trying to send. The effects were immediate and dramatic. Across Europe and North America, telegraph systems began to fail catastrophically. Messages became garbled, then ceased altogether. The sensitive instruments in telegraph offices, designed to handle tiny electrical impulses, were suddenly overloaded with raw power from the sky. The anecdotes from telegraph operators around the world paint a vivid picture of the chaos. In the United States, on a line connecting Boston and Portland, Maine, a telegraph operator named Dr. Aaron B. Cornell was trying to send a message when he found his equipment behaving strangely. He quickly realized the problem wasn't with his local power supply. In fact, he disconnected his battery, the device that provided the electrical current to his telegraph line. To his astonishment, the line continued to function. Messages could still be sent and received, powered not by his battery, but by the celestial electricity flowing through the wires. Cornell was reportedly able to operate his line for 2 hours using only the aurora-induced current. It was an unprecedented and bewildering experience. He read and sent messages at 100% normal speed without any local power source, literally running his office on the energy of the solar storm. Similar incidents were reported across the globe. In England, telegraph offices experienced sparks flying from their equipment. Operators who attempted to send messages reported receiving electric shocks through their fingers as they touched the keys. One operator in Norway described a stream of fire pouring from his telegraph key. In some extreme cases, the surges of current were so powerful that they ignited the paper rolls used to read out messages, causing small fires in telegraph offices. Imagine the scene. An operator, perhaps admiring the brilliant red sky outside, suddenly having to deal with their equipment sparking violently and emitting smoke, all while trying to decipher garbled messages that seem to be coming from nowhere. These powerful, uncontrolled currents posed a significant danger to the operators themselves and the fragile equipment. While there were no recorded fatalities directly attributed to the Carrington event, many operators received painful shocks. The delicate relays and wires within the telegraph machines were fried, leading to widespread damage that took days, and in some cases weeks, to repair. The global communication network, which had been celebrated as a triumph of human ingenuity, was brought to its knees by an invisible force from the sun. The events of September 2, 1859, were a wake-up call, though few at the time fully understood its implications, foreshadowing a vulnerability that would only grow exponentially with technological advancement. The awe-inspiring light shows and technological chaos of 1859 left the world bewildered. People could see the effects, but they had no way of understanding the cause. The science to explain it simply did not exist yet. Today, thanks to more than 160 years of scientific advancement, we can look back and piece together exactly what happened. We first need to update our image of the sun. It is not a calm, steady ball of fire. It is a dynamic and incredibly violent place, a giant sphere of superheated gas called plasma, governed by unimaginably complex and powerful magnetic fields. These magnetic fields are constantly twisting, stretching, and snapping. The dark sunspots, like the one Richard Carrington was observing, are the visible signs of this intense magnetic activity. They are areas where the magnetic fields are especially strong, and they are the breeding grounds for solar storms. The event itself happened in two distinct stages. The first stage was what Carrington and Hodgson saw, the solar flare. A solar flare is an enormous explosion on the sun's surface, a sudden and intense release of energy. Think of it like the muzzle flash from a gigantic cannon. When the tangled magnetic field lines above a sunspot suddenly snap and reconnect, they release a tremendous amount of energy in the form of radiation, which includes everything from radio waves to X-rays and visible light. This radiation travels outwards from the sun at the speed of light. On September 1, 1859, this flash of radiation from the flare reached Earth in just over 8 minutes, and the tiny sliver of it that was visible light is what appeared as those brilliant patches in Carrington's telescope. This flare was the warning shot. But while the flare is the bright, flashy part, it's the second stage of the event that carries the real destructive power. The flare was just the flash. The real danger was the cosmic cannonball that followed. This is what scientists call a coronal mass ejection, or a CME for short. A CME is a colossal eruption of matter from the sun. It's a gigantic cloud of plasma, billions of tons of electrically charged particles, all bound together with its own tangled magnetic field, hurled out into space at incredible speeds. The same magnetic explosion that caused the flare also launched this massive cloud of solar material directly towards our planet. Under normal circumstances, a CME takes several days to travel the 93 million miles from the sun to the Earth. A typical journey might take anywhere from 2 to 4 days. But the CME associated with the Carrington event was exceptionally fast. It made the entire trip in just 17 hours and 40 minutes. For a long time, scientists were puzzled by this incredible speed. The current leading theory is that the path for this CME had been cleared by a previous, smaller CME that had erupted from the sun a few days earlier. This first CME acted like a snowplow, clearing a path through the solar wind, the stream of particles that constantly flows from the sun. This cleared path allowed the much larger, faster Carrington CME to travel through space with far less resistance, like a car on an empty highway, enabling it to reach Earth in record time. When this superfast, massive cloud of plasma and magnetic fields finally arrived, it slammed head-on into the Earth's own magnetic field, known as the magnetosphere. The magnetosphere is our planet's invisible shield. It's generated by the molten iron core of our planet, and it extends thousands of miles out into space. Its job is to deflect the solar wind and protect us from harmful solar radiation. But the Carrington CME was no ordinary solar wind. It was a tsunami of solar matter. The impact was so violent that it compressed our planet's protective shield down to a fraction of its normal size. This sudden, violent compression and the chaotic interaction between the CME's magnetic field and Earth's magnetic field is what we call a geomagnetic storm. As the CME enveloped our planet, it injected a huge amount of energy and particles into our upper atmosphere. This is what caused the spectacular auroras. The charged particles from the Sun were guided by Earth's magnetic field lines towards the poles, where they collided with oxygen and nitrogen atoms in the air. These collisions excited the atoms, causing them to glow in those brilliant shades of red, green, and purple. Because the storm was so immensely powerful, it drove these particles much further from the poles than usual, which is why the auroras were visible in tropical locations like Cuba and Hawaii. The storm also explains the chaos on the telegraph lines. A fundamental principle of physics, discovered by Michael Faraday, is that a changing magnetic field will induce an electrical current in any conductor. During the Carrington Event, the Earth's magnetic field was fluctuating wildly under the assault of the CME. The thousands of miles of long copper telegraph wires strung across continents acted as giant, unintended antennas. The rapidly changing magnetic field induced powerful, uncontrolled electrical currents in these wires. These geomagnetically induced currents overwhelmed the low-voltage telegraph systems, causing sparks, shocking operators, and, in some cases, providing enough free, raw electricity from space to run the equipment even when the batteries were disconnected. The world of 1859 was shattered by the Carrington Event, but it recovered quickly. Within a few days, the auroras faded, the strange currents disappeared from the telegraph wires, and the damaged equipment was repaired or replaced. The world moved on. For the people of that era, it was a fascinating and disruptive curiosity, but it was not a civilization-ending catastrophe. The reason is simple: their civilization was not built on a foundation of electricity. Their lives were powered by steam, muscle, and candlelight. The telegraph was a marvel, but its failure was an inconvenience, not an existential threat. Now, imagine a storm of that same magnitude striking the Earth today. The outcome would be profoundly different. Our modern world is a delicate, intricate web woven from electricity and digital information. From the moment we wake up to the moment we go to sleep, our existence is supported by systems that are critically vulnerable to the very same forces that crippled the telegraphs of 1859. The single greatest point of failure is our electrical grid. The long, high-voltage transmission lines that stretch for thousands of miles across our continents are, in effect, gigantic versions of those old telegraph wires. When a powerful geomagnetic storm hits, these lines would absorb massive, uncontrolled currents from the Earth itself. These geomagnetically induced currents would flow into the thousands of large power transformers that are the heart of our grid. These transformers are designed to handle specific voltages with incredible precision, but they are not built to withstand a sustained onslaught of direct current from the ground. The result would be catastrophic. The internal windings of these transformers would rapidly overheat, melt, and fail. The problem is that these are not off-the-shelf items. A large power transformer can be the size of a small house, weigh several hundred tons, and cost millions of dollars. They are custom-built, and the manufacturing process can take anywhere from 12 to 24 months. The world has a very limited manufacturing capacity for them, and we have very few spares in reserve. A Carrington-level event could potentially destroy hundreds of these critical components across an entire continent simultaneously. The consequence would be a widespread, indefinite loss of power that could last for months, or, in the worst affected regions, potentially for years. Without electricity, modern society grinds to a halt. The cascading failures would begin almost immediately. Water purification and pumping stations would stop, cutting off the supply of clean drinking water to cities. Sanitation systems would fail. The entire food supply chain would collapse, as refrigeration for storage and transport would disappear. Banks would be unable to function. Electronic transactions would cease. Gas pumps require electricity to work, so transportation would be paralyzed. Hospitals would have to rely on emergency generators, but those generators would eventually run out of fuel. It is a grim but realistic scenario. And that is just on the ground. In space, our vulnerability is just as acute. Our global infrastructure is utterly dependent on a constellation of thousands of satellites orbiting the Earth. These satellites provide our global positioning system, or GPS, which guides everything from airplanes and container ships to your car's navigation system and the precision timing required for financial market transactions. A severe solar storm could fry the sensitive electronics on these satellites, damage their solar panels, or even cause their orbits to decay, turning our vital orbital infrastructure into a field of space junk. Communication satellites that relay television signals, phone calls, and internet data would also be at risk, potentially silencing our globally connected world. So, are we simply waiting for this inevitable disaster to strike? The answer, thankfully, is no. While our vulnerability is greater than ever, so is our ability to see the danger coming. The field of space weather forecasting has made incredible strides. Organizations like the National Oceanic and Atmospheric Administration's Space Weather Prediction Center in the United States, along with similar agencies around the world, act as our planetary watchdogs. They have a fleet of sophisticated satellites, our eyes on the sun, that monitor it 24 hours a day, 7 days a week. Missions like NASA's Solar Dynamics Observatory send back constant high-definition images of the sun in multiple wavelengths of light, allowing scientists to see the formation of volatile sunspot regions and the buildup of magnetic energy. Most critically, we have spacecraft positioned 1 million miles away from us, in a direct line between the Earth and the sun. Satellites like the Deep Space Climate Observatory act as our tripwire. They can detect a coronal mass ejection as it leaves the sun and streams towards us, giving us a precious, though brief, period of warning before it hits. Depending on the speed of the CME, this warning could be anywhere from 50 minutes to an hour or slightly more. That warning time is crucial. It would not be enough to stop the storm, but it would be enough to try and brace for impact. Power grid operators could take protective measures, such as rerouting power, taking sensitive systems offline, and strategically disconnecting parts of the grid to prevent a continent-wide cascading failure. Satellite operators could put their spacecraft into a protective, safe mode, turning off non-essential components to reduce the risk of electrical damage. We're also slowly beginning the process of hardening our infrastructure. This involves developing new technologies to block the damaging currents from entering transformers and building more resilient satellite electronics. But this process is incredibly expensive and slow. We look back at the Carrington Event of 1859 as a historical curiosity, but it was also a warning. It was the first time that our own technology acted as a sensor, revealing a powerful and unpredictable aspect of our star's nature. The story of Richard Carrington, a lone astronomer making a careful drawing, has evolved into a global effort to understand and predict the sun's behavior. The Carrington Event reminds us that we live in a cosmic environment, subject to forces far greater than our own. The next great solar storm is not a question of if, but a question of when. Whether we experience it as a manageable crisis or a civilization-altering catastrophe will depend entirely on the foresight, preparation, and investment we make today. It is a profound challenge, a race between our growing technological dependence and our scientific understanding of the star that makes it all possible. This podcast was entirely produced by Andrew Scott. If you have any suggestions for topics or improvements, please get in contact.